Greetings from Urbana, Illinois, where it is currently a balmy 12 degrees Fahrenheit. In this video, we're going to go through our second topic of mathematical preliminaries, this topic of convexity. And we're going to start off by talking about what are convex versus concave shapes. This is probably a term that you've heard before, but it turns out there is a very precise mathematical definition of convexity and concavity. We're going to talk about something called convex sets. We're going to go through a hyperplane example. We're going to talk about feasible domains for a particular type of continuous optimization known as linear programming, or LPs. And in LP, the objective function and all of the constraint functions are linear, and convexity plays a role in linear programming. We're going to then move on to this complementary topic of convex functions. There is a relationship that we're going to see between convex sets and convex functions, and both of these are important with respect to the mathematics of optimization. We're going to go through what's called an epigraph definition of a convex function, which, at least in my opinion, seems to be a very intuitive way of understanding convex functions. And then we're going to go through the relationship between convex sets, functions, and mathematical optimization. So what is a convex shape? You've probably seen convex versus concave lenses. For example, here on the left we have a biconvex lens, which means on both sides we have this convex shape that's bulging out toward the middle. And then on the right we have this biconcave lens, which means on both sides we have this curve inward. We're going to get more precise and mathematical about what we mean by convex. Another application of convexity is something that's familiar to backcountry skiers or other people who venture into avalanche terrain. One of the features that is riskier and that in some cases needs to be avoided are what we call convexities. So if you have a slope that has this convex shape, then there's a chance that you could have a weakened zone of the snowpack and have an increased probability of an avalanche in that zone. In contrast, you can have a concavity, and that has very different properties compared to a convexity. Here's an image of a mountain range in Alaska that shows a section that's highlighted here where the wind has built up a deeper layer of snow on top of a convexity in the slope. And so this is an example of the type of feature that a skier or other backcountry users should avoid if they are venturing into avalanche terrain. We're going now to address these questions. What are the mathematical definitions of convexity? And how does this relate to optimization? We're going to switch over to the drawing pad. I'm going to work through the course notes on the topic of convexity. We're going to start off with the mathematical definition of a convex set. One way of thinking about this is in a two-dimensional space of real numbers. Suppose we have two real numbers, x1 and x2, and we can define a point somewhere in that space, but we can also define a set of points. If I were to define a boundary and said that all of the points that are on this boundary or inside the boundary are in some set, and that comprises an infinite number of points in this two-dimensional space. We can now start to define what convexity is. A set is convex if a line connecting any 2 points in the set stays in the set. For example, if I have a set of points that looks like this, and if I were to identify any 2 points that are within this set and then draw a line in between those points, if that line always stays in that set, then I can say that this set is a convex set. Let's go through a couple of examples that are not convex sets. So the first set that I drew is actually not a convex example. So if I have these 2 points, both of which are in the set, but then I draw a line in between those points, that line goes outside of the set. That's sort of like this biconcave lens example that we looked at. If I draw the shape of the lens, then if I was thinking of this lens as a set of points, and I were to select a point here and a point here and draw a line in between, well, that line exits the set. So this biconcave lens is not a convex set. There are other ways we can have non-convexities. What if we have a convex set here and a convex set here? But what if I define the set of points to be the combination of these 2 sets? So in that case, this point is in the set, and then this point is in the set. And if we draw a line in between them, then we can see that this is not a convex set. This is a great way to conceptualize what convex sets are, or non-convex sets. But we can use other tools that are more mathematically rigorous to actually say something about specific sets and test whether they are convex or not. One of the most helpful tools is to use a particular definition of a line between 2 points. Suppose I'm going to label this point here x1. And that's a 2-dimensional point if we're talking about a set of points on a plane. And then here, I'm going to label this x2. I want to define the set of points that are on the line that connect x1 and x2. One way of thinking about it is starting at one of these points and then traveling along the line toward the other point. How might we do that? Well, one way is to define a scalar parameter, lambda, such that it describes how far along this line we have moved between x1 and x2. If I'm roughly 30% of the way between x2 and x1, lambda is equal to 0.30. How would I use this to define this general set of points on this line between x1 and x2? Here, if x is a 2-dimensional vector, and then I write this summation of lambda times x1, the point x1 up here, plus 1 minus lambda times the point x2, and then I consider a range of values for lambda between 0 and 1. If we sweep through all the values of lambda in this range, then we are going to traverse the line between x1 and x2. Let's have a little bit closer look. What happens if lambda is 0? If lambda is equal to 0, then x is going to be equal to x1 times 0, so that term goes away, plus 1 minus 0 times x2, or x2. So at lambda equals 0, we are at x2. And you can see similarly that if we are at lambda equals 1, then we're at x1. And if we're somewhere in between, you can go through to see that, yes, we are in fact at a point on this line in between these 2 points. And this goes beyond just a 2-dimensional case. This concept applies to an n-dimensional space. So even if you can't visualize it, we can still use this concept of a line connecting 2 points within a set. And even if we can't visualize it, there may still be ways of determining whether that line goes outside the set or not. Let's have another quick example. Suppose this is a set of points in 2 dimensions. Here is x1, here is x2. Here's the line that we want to define. And at x1, this is where lambda is equal to 1. x2, this is where lambda is equal to 0. And suppose at a point that's halfway between x1 and x2, this is where lambda is equal to 1/2. This concept, as I mentioned, extends to the case where we have more than 2 variables. When we're thinking about things that we can't visualize, shapes like lines, one of the terms that's often used is hyper, or A hyperline is a line that is in a space that is of greater dimension than 3. We can no longer visualize it, but it exists, and we can use these kinds of formulations to quantify the line in this higher dimensional space. Let's talk about hyperplanes as an example. So sort of like we can have a hyperline, which is a line in a space of dimension greater than 3, we can also talk about hyperplanes. A plane that we are all familiar with is going to be a straight flat surface that's in a 3-dimensional space, but to traverse around that plane we only need 2 quantities to specify where we are on that surface. We can extend this concept of a plane to higher dimensions, but we're going to visualize it here just using a line as a plane, but the way we're formulating this extends to n greater than 3. So suppose we have a plane. This line is what is representing our plane. And one way of defining a plane is to specify a point. I'm going to call that x0, and then a vector that emanates from this point and is perpendicular to the plane, or orthogonal to the plane. So we have this vector A and a point x0 all in Rn. If we're thinking about this 2-dimensional drawing, then n is equal to 2, but this extends to any finite number of dimensions. Let's define an additional point in the plane. I'm going to call this x1. We want a way of defining any arbitrary point that is in this plane. One way of doing that is to define a vector that points from x0 to a point that is in the plane, and I'm going to define that vector as c equals x1 minus x0. By definition, the vector A is going to be orthogonal to the vector C. And if you think back to linear algebra topics, the dot product, the inner product, A dot C, that is going to be equal to 0. That's going to be true regardless of the dimension of the space that we're operating in. Just by definition, we're saying that C and A are orthogonal vectors. And so using this property is one way of defining a hyperplane. If we were to expand this out, if we were to take this definition of C equals x1 minus x0, then that's going to help us get to a more general definition of a hyperplane. So if we substitute in what the value of C is, this x1 minus x0, then we're going to end up with the vector A dot x1 minus A dot x0. And that's going to be equal to 0. Let's suppose that x0 is a point that is fixed. It doesn't change. This is part of the definition of our hyperplane. So this part, that second term, is going to be a constant. Let's say that is equal to b, and then we can rewrite this as a dot x1 is equal to b. For any point that is on this hyperplane, we can use this relationship to express that point. So any point x1 or some other point that is on the plane, if we find the inner product between that point and the vector A, the value is going to be this constant value of b, which is equal to a dot x0. One way mathematically of describing this is to write this is the set of all values x such that the following expression is satisfied. A transpose x is equal to b. That's a nice, precise mathematical definition of a hyperplane. With this defined, we can ask the question, is a hyperplane a convex set? So you can think about this in 2 or 3 dimensions and just try to conceptualize whether this is a convex set or not. So think back to the original definition of a convex set. If we have any 2 points in a set and connect a line between them, and that line always stays in the set, then we can say, yes, this is a convex set. But if there's even one counterexample where 2 points that are in the set and a line connecting them goes outside of the set, then it is not a convex set of points. How do we show whether something is a convex set or not? If we are just thinking about this intuitively, it really is impossible to think of any counterexample where there might be 2 points on a plane or a hyperplane and a line connecting them actually goes outside of the set. Just based on that intuition, we can at least imprecisely say that a hyperplane is a convex set. But one question is, can we actually prove it? So I'm not going to go through this in detail right now, but I encourage you to have a look at the notes and make sure that it makes sense to you. But the basic idea is take the definition of a hyperplane and then take the definition of a line connecting 2 points, the formula that we just went through that involves lambda, and see if it's possible to show that for any 2 points that are in this set using this definition, then any point generated using the formula for the line is also going to be in the set. And if you can show that it's true for any arbitrary point that's in the plane, then yes, a hyperplane is a convex set. So please go through those notes, make sure that makes sense. The notes step you through the proof for that. But here I want to introduce another question using another type of entity that's similar to a hyperplane, but instead of a hyperplane, it's called a half space. And the definition is only slightly different to the hyperplane. I'm going to define this quantity h to be a set of points that comprise a half space. And I'm going to write that to be equal to the set of points x, such that A transpose x, where A is some vector, that's the same length as x, is instead of equal to B, less than or equal to B. So what that essentially means is if we say are in a two-dimensional space and this is the plane that we would define if this was an equality here, then that shows up someplace in this two-dimensional space. But then depending on the directionality of the inequality, one side of this plane is going to be in the set and one side is not going to be in the set. One quick way of testing that is to check the origin, plug in the 0 vector, and see whether that satisfies this inequality or not, and then you can see if the origin is in the set. If it's not, suppose it's not the case, then I'm going to draw these hatch marks to indicate that these points are not in the set. And suppose we have our point x naught and then A, and of course if we go back to the definition of x naught, that's going to be A dot x naught equals B. So if we're starting off with the value of B, then we could extract out what is the value of x naught if needed. In any case, we need a point and a vector to define what a half space is, and the half space involves this directionality. Then we can ask this same question about convexity. Is a half space, so all of the points out here, is this half space a convex set? Think about the definition of convex set. Can you think of any counterexamples? Are there any points that are both in this half space such that if we connect those 2 points, the line, well, that's supposed to be a straight line, the line goes outside the set? Intuitively, a half space is a convex set. But again, that is not a proof. So it may be a useful exercise for you to go through and use the definition of a half space, and then also go through and use the definition of a line that connects 2 points that we've used already, and then see if it's possible to show whether two arbitrary points in a line connecting them might actually venture outside of the half space. That's something that is possible to prove. And in this class, we're not focusing on proofs. It's not a proof-based course, but sometimes at least thinking through some of these proofs can be very helpful in generating some insights about the underlying mathematics related to optimization. I mentioned a few moments ago that one type of continuous optimization problem is a linear program. And a linear program, or an LP, has a linear objective function and linear constraints. And there are a few different ways of expressing a linear program. Here is one. Here we have a linear objective function where we have a fixed vector c that's the same length as x, and sometimes this is referred to as the cost vector. It basically weights or penalizes values of x. We want c transpose x, or the dot product between c and x, to be as small as possible. And in this formulation, we are using one possible definition of constraints where we have a set of inequality constraints. We have a times x, so A is a matrix, so if x is of length n, let's say m is the number of constraints, and n is the number of variables, so then c and x have the same length, they're both of length n, and b, the right-hand side of this constraint vector, that's going to be in Rm. It's going to have the number of linear constraints as its length. And then if we're thinking about this multiplication, a times x, and that's going to have length b. So say this is b, this is a, this is x. Length of x is n, and the number of columns in A is going to need to be consistent with x, and then b is length m, and then therefore A is the number of rows m by the number of columns n in dimension. We can have some number of constraints m, and m could be different from n. Something to observe here that's interesting is that the way we've defined the constraints here in this linear program basically amounts to a set of half spaces. If we think about one of these constraints, if we just think about one of the rows of A times x, then that's sort of like our A transpose x is less than or equal to b. If A is one of the, lowercase a is one of the rows of the matrix A, then we can split it out into these different individual constraints. And with that conceptualization, we can think of the feasible domain of a linear program as a composition of these half spaces. So let's visualize what that actually means. Suppose we have a two-dimensional space. There's x1 and x2. And we've visualized what a half space is before. Suppose here's a half space. I'm going to say all the points on the other side of this cross-hatching are in the half space. Or in other words, everything on this side is infeasible with respect to the single constraint that corresponds to this half space. Now, if we have multiple constraints, we're going to have multiple half spaces, and in a well-posed problem, these constraints are going to be linearly independent of each other, and we can have some kind of composition of these constraints where we're basically cutting off pieces of the space by defining and adding each of these half spaces. And so here, these two lines are not parallel. Eventually they would intersect, but here I'm going to just, for convenience, define another half space right here. And if we take all of these combined together, it's this interior that is the feasible domain. Or in other words, this is the set of points, x, that satisfy all of the linear inequality constraints simultaneously. And in our linear program, our job is to figure out well, which one of these points minimizes our linear objective function? And if we have a linear objective function, think to yourself, what would the level sets of a linear objective function look like in two-dimensional space? It's going to turn out to be just straight lines. So let's suppose these are level sets of the objective function. And suppose that this is the decreasing direction, or in other words, the gradient of f of x points the other direction, that points the uphill direction. And we're going to see in the next section that the gradient of c transpose x, if we just graphically think about moving in the decreasing direction, keep going downhill, the idea is we want to find what is a point that's in this set, the feasible domain, that satisfies our constraints, ax less than or equal to b. And if we keep moving down, say we move down here, we hit this edge right here, is it possible to reduce the objective function even more without crossing over into the infeasible domain? Well, we could move along this constraint boundary and keep going downhill. And it looks like at this vertex, the way that I've defined the direction of decrease for f of x, looks like that's going to be the minimum. So this is a long explanation to give you some insight into what a linear program looks like. For those of you who've already taken an Introduction to Operations Research class, you've already seen this before, at least in some form. The main reason for bringing this up here in our discussion of convexity is to address this question of whether the feasible domain for a linear program, at least defined this way, is a convex set. So let's focus on this feasible domain here and think about this question. Is it possible to define 2 points somewhere in the feasible domain of a linear program and draw a line between those points and have that line go outside? We're not going to prove it mathematically now, but at least conceptually, think about any possible way of constructing a linear program feasible domain by cutting off parts of the space using these half spaces. We can only take these straight cuts off of the space. We can't use curves, and there's no way to create a feature like this with a linear program. Suppose I'm defining this as a constraint. If the feasible domain for the linear program is defined by a composition of half spaces, we can't get this sort of behavior because we would have this half space continuing out this way and this half space continuing out this way. And so then the resulting smaller feasible domain, that would be convex. Conceptually, we can say that the feasible domain of a linear program is a convex set. And that turns out to be a really important property when it comes to solving linear programs. It's a very nice property. Suppose now we are looking at the feasible domain of a nonlinear program. This is different from a linear program where all of the constraints are planar. And in this case, we can have general nonlinear constraints, and these will appear or could appear differently when we are looking at the optimization space. And because of the possibility of them being curved, we can get feasible domains that have very different properties. So suppose we have, again, a two-dimensional optimization space. And let's suppose we have 2 nonlinear inequality constraints. With these 2 nonlinear inequality constraints, I have sketched out the curves, or the set of points in this x1, x2 space where those constraints equal 0. And depending on the direction of the inequality, one side or the other of these curves will be feasible or infeasible. So the way I've sketched this outside of these curves is infeasible. So inside here is the feasible domain. Think about this shape and let's address the question, is this a convex set or not? I can provide a very quick counterexample with these 2 points. Those are both in the set. if I draw a line between those 2 points, the line leaves the set. So therefore, this is not a convex set. And if we have non-convex feasible domains in a nonlinear program, that can have a big impact on the nature of the problem and what we can say about the solution to these problems. Okay, we've talked about convex sets. Now let's talk about convex functions. These are also important for optimization theory. I'm going to start off with a standard mathematical definition of a convex function, and then we're going to move to another way of defining convex functions that, at least for me, is conceptually easier to understand. We can say that a function, f of x, is convex if 2 things are true. First, the set of all points where this function f is defined, that set must be a convex set. In a lot of cases, the domain might just be the appropriately sized or the right dimension set of real continuous numbers. And in that case, the space Rn, that is a convex set, and so that is going to help us. What if we have a function where there is some combination of values that are invalid for this function? In that case, so for example, what if we're taking the square root of a number and we can't have negative numbers if we're not allowing for imaginary numbers? That's a case where we might have something other than the whole set of real numbers in the appropriate dimension as the domain of a function. Whatever the domain is, the first step is we need to verify that the domain of the function is a convex set. And then, in addition to that, a second requirement must be satisfied. This next part is a little bit more complicated to go through, but the basic idea is we need to have a look at 2 points that are in the domain of f. And as we have needed to verify in part 1, that domain must be a convex set. And this is a little bit different from just looking at, say, whether a line connecting these 2 points stays within a set. It involves this particular inequality constraint. Thinking back to the definition of a line that we've used before, on the left-hand side, we're looking at values of lambda such that we are going across a line between x1 and x2. And we are requiring here that the function value of any point along this line connecting x1 and x2 is going to be less than or equal to this quantity. So what is this quantity instead? Well, here we're looking at the value of f of x1 and the value of f of x2. But this looks sort of like drawing a line again, but it's a little bit different. We're actually now looking in the combined space of x and f of x. I think it helps to visualize this to really see what's going on. To make this visualization easy, let's start with a univariate case, or f is a function of a single variable, a scalar variable x. And here I've defined a continuous function, f of x, this curve, and then 2 points in the domain of f of x, x1 and x2. And we're going to use this to understand what this inequality relationship means. So on the left-hand side, we're looking at a function value at a point between x1 and x2. So in other words, we're looking at the actual value of the function as we are traversing from x1 to x2 in the space of input arguments. And then we want to make sure that this value, this darkened line here, it is always less than whatever this quantity is, Well, so what is that quantity? Here we're looking at the point f of x1 right here and the point f of x2 right here. And if we're looking at lambda that's varying between 0 and 1, then this actually forms the line that cuts across this space between those 2 points. Now maybe you can see what this inequality requirement is. That means that this curve, actually on the function surface, must always be less than or equal to the line that connects these 2 points on the surface. And in this case, because this function is always underneath this line, and this is true for any 2 points that we can identify in the domain of f, then yes, this is a convex function. What's an example of a non-convex function? What's a counterexample where this inequality requirement is not satisfied? Suppose again we have a single variate function, and in this case I'm going to define f of x with a different shape. And suppose this is x1 and this is x2. Here is f of x1, here is f of x2, and we need to compare the actual function value along this curve between x1 and x2 against a line that connects these points x1 and x2 in the space that includes the output of f. In this case, we can see that this function value, or in other words, the left-hand side over here, is clearly greater than the line that connects x1 and x2. We have violated the requirement for a convex function, and so therefore this function is not convex. To use an alternate definition of a convex function, we need to understand something called the epigraph of a function. I'm going to define it here mathematically first, and then we're going to look at it graphically to try and get some better intuition for what an epigraph is. So the epigraph of a function is the set of all points, this composition of x and t, that are in the set of real variables of dimension n plus 1. And it's n plus 1 because we've taken x, which is of dimension n, and we are augmenting it with an additional variable t. So here we have this n plus 1 space, and we're looking for all of the points in this space such that x is in the domain of f, and our value of this additional variable t is always greater than or equal to f. So what does this mean? Let's suppose we have a univariate function. So n is equal to 1 and n plus 1 is equal to 2. And suppose we have a function f of x, and we want to figure out what points are going to be in the epigraph of f of x. We can choose any point along the x-axis. In this case, I'm assuming all values of x are in the domain of f. But then we need to choose a value of t such that it satisfies this requirement. So we're looking at combinations of values of x and values of t that have this requirement that depends on f of x at this given point x. So suppose I'm looking at a point x1, and that's in the domain of f. So we've satisfied this first part. But now we need to choose a value of t such that it is greater than or equal to f of x. And we can do this visually. If I were to choose a value of t, say, right there, well, that is less than f of x, which is right there. And so this candidate value of t, that does not satisfy this requirement, so it is not in the epigraph of f. But if we keep going up, then the first point that is in the epigraph is the point that's on the function line. And then if we keep going up in value for t, then these points are also in the epigraph because those values are larger than the value of f of x at this point x1. So everything up above, that's in the epigraph of x. And if I were to repeat this for another point, say x2, I could do the same thing. And if I were to do this an infinite number of times across the entire domain of f, we could discover then that the epigraph of f of x is essentially the set of all points that are either on the curve f of x or above the curve f of x. So this is the epigraph of f. The really useful thing about epigraphs is it helps us to conceptualize whether a function is a convex function or not rather rapidly. And that is because it's possible to show that if the epigraph of a function is a convex set, then that function must be convex. Or in other words, f of x is a convex function if and only if the epigraph of the function x is a convex set. We're not going to prove that here, but it's a really useful conceptual tool. So now let's think about the epigraph here, all these points here, and think about whether that set is a convex set. So we have a lot of points that are much larger than what we're visualizing here in this plot, but very quickly we can see that f of x is not a convex set. So for example, these points, f of x1 and f of x2, these points are both in the epigraph of f. And if I were to draw a line between those 2 points, that line goes outside of the epigraph. So therefore the epigraph of f is not a convex set, and therefore f of x is not a convex function. If we were to draw some other function that is convex, and then think about the epigraph of this, no matter how many combinations of points that we choose in the epigraph, if we connect a line in between them, it's going to stay in the set that is the epigraph of f. When we were looking at convex sets a few minutes ago, it was maybe a little conceptually easier because those were all bounded sets. The sets that we're using here to test f of x, these epigraphs, these are unbounded sets. It's still a valid set, and it's still something that we can test whether it's a convex set or not, but it's conceptually a little bit different than what we looked at before, and I just wanted to acknowledge that. Let's talk a little bit about the relationship between convexity and mathematical optimization. We're going to talk first about unconstrained optimization. There's a really nice property in unconstrained optimization if we can say that our objective function that we're trying to minimize, say we're calling that f of x, if f of x is a convex function, then any minimum that we find, any minimum that satisfies optimality conditions, any local minimum will also be a global minimum. So for example, if we have a univariate function and we have a convex objective function and we find a minimum, then that minimum is guaranteed to be the global minimum. And this is a nice property to have. It's one way that we can prove global optimality, but it's not always easy to identify optimization problems that are convex like this. In practical engineering design optimization, often the problems that we're dealing with are non-convex problems. And we'll explain shortly in a little bit more detail what we mean by a convex problem, and that depends on the relationship of convex functions and of convex sets. If we have this case where we have a single local minimum, and that's pretty obvious that it's also the global minimum. I worded this assertion about global optimality in a very specific way. I said that any local optimum will be a global optimum. That implies there's the possibility that we could have more than one local optimum that will also be the global optimum. We can have a quick look at a simple example that explains this concept. Suppose we have, again, a univariate function that is convex, but what if it has, that's supposed to be flat, a flat spot in the middle? So the derivative through this area is 0. Any of these points in this flat area will satisfy the requirements to be a local minimum, because there's no direction we can move such that we can decrease the objective function anymore. But we have this set, this infinite set of local minima, and we have a convex function. You can think through this and verify to yourself that this is a convex function, or we can use the epigraph approach and make sure that is a convex set. This is a convex function, and we have an infinite number of local minima. Well, all of those minima are global minima because they're all the same. So that's a possibility, and this can arise in higher dimensions as well. Say if we have a problem with 2 dimensions, then if we have a line that we can follow in this 2-dimensional space where it's flat, then that's also going to be a case where we could have a convex function with multiple local minima that are all global minima as well. We can add the additional statement that if there are no flat spots in the function and a function f of x is convex, then there exists a single local optimum that is also the global optimum. If we're talking about unconstrained optimization, we say that an unconstrained continuous optimization problem is a convex problem if the objective function is a convex function. This is a little bit more complicated when we move on to constrained optimization problems. If we move on to more general nonlinear programs that have constraints, in addition to the objective function being a convex function, for this to be a convex problem, we also need to satisfy the second requirement that the feasible domain, or in other words, all of the points that satisfy all of the constraints simultaneously, is a convex set. Think back to the linear programming example. We were drawing all of these half spaces intersecting, and these form a feasible domain, and we talked through how this feasible domain here is a convex set. That's important because then that helps us to identify when we have a convex constrained optimization problem. In the example of a linear program, we've already seen how the feasible domain is a convex set. And if we have an objective function that's linear, it's also possible to show that the objective function is a convex function. So therefore, a general linear program that has a linear objective function and linear constraints is going to be a convex problem. So if we find a local minimum to this linear program, then it's going to be a global minimum as well. Let's have a look at an example where we have a nonlinear objective function, and the way I've drawn these level sets, this looks like it could be a convex function. I'm going to assert here that f of x is indeed convex, and if this was an unconstrained problem and we found this minimum and we could show it's a minimum, a local minimum, because the gradient is equal to 0, then we could also say that it is a global minimum. Now, what if we add in a constraint? And then we have a look at what the feasible domain looks like and whether that's a convex set or not. If we were to add in, say, only linear constraints, these half spaces, like as in a linear program, then we would also have a convex set as the feasible domain, and then we could assert that any local minimum is going to be a global minimum. But what if we go to a nonlinear constraint? Well, one nonlinear constraint might look like this. What if the infeasible side is on the side where the unconstrained minimum is? And then just graphically we could see, trying to go as far downhill as we can without violating this constraint, then we're going to have a minimum right here. And I've not sketched out the entire domain or entire feasible domain, but I could also assert here that this feasible domain is a convex set, and then we could assert that yes, in fact, this local minimum is also a global minimum. Let's change things up. What if we have a constraint, a nonlinear constraint, that looks a bit different? Here, the feasible domain is non-convex. It's pretty easy to show that, choosing a couple of points that are feasible in the feasible domain and drawing a line between them, and that line goes outside of the feasible domain. And one property of this, the way I've drawn it, is we can see, oh, there's a local minimum right about there. But if we are starting from this direction and we're going downhill, we'll get to this point, and there are no more downhill directions. If I keep moving this way, it's going to go uphill. It's going to increase the objective function value. So this is a local minimum, and this over here is also a local minimum. This local minimum over here is definitely not a global minimum, because we can visualize that here another local minimum is at a smaller level set value than the local minimum on the right. And so this is an example of how, when we have a non-convex feasible domain, we could have the possibility that we have a local minimum that is not also a global minimum. This is the last topic in convexity that I plan to cover here. We're going to return to it a number of times as we move through other topics in the semester. Thank you.